Hello everybody, Rob here, and welcome to module number 3, Understanding pH. In this module, we are going to go a little deep, okay? We're going to get a little bit scientific here. We're going to get a lot deeper than we probably are going to want to introduce the water to someone with, but I want to really give everyone here a better understanding and a more in-depth understanding and knowledge of these concepts. That way, if potential clients or your downline ever want to know more, they can come to you and you can guide them and you can give them that broader understanding. Okay, because with that understanding, you will be able to answer tougher questions, and then you will be able to reduce the skepticism and increase the confidence, okay, in your downline and in potential buyers. Okay, so let's get started on the exciting information of pH. Okay, so most of us, if not already, have seen videos or are aware of the pH scale. Okay, so it's from 0 to 14. Okay, 7 being in the middle, which represents neutral. Okay, and just like the pH drops that we put in the waters on a Kangen demo, okay, red to yellow to the green, the red would be the most acidic, orange, yellow, okay, and then we got green in the middle for neutral, and then we get light blue to the darker blue to the purples, and that's representing the pH scale, okay? And by using the drops, it's a visual, and it gives a visual indication of where the pH is in a solution or a water. Okay, so we're gonna talk about the scale here for a little bit. Okay, the scale is logarithmic, okay? This means that the difference between a whole value on the scale represents a multiple of 10, okay? Example, a substance with a pH of 5 is 10 times more acidic than a substance with a pH of 6, okay? Because it's logarithmic. So if you go from 5, if you go from 6, something with a pH of 6, and you have a substance with a pH of 5, because it's logarithmic, the substance with a pH of 5 is 10 times more acidic than the substance that's a pH of 6. Okay, another example, a substance with a pH of 9 is 10 times more alkaline than a substance with a pH of 8, okay? Because the scale is logarithmic. So if a substance has a pH of 10, it is 100 times more alkaline than a substance with a pH of 8. Another example, a substance with a pH of 2, okay, so it's very acidic, is 10,000 times more acidic than a substance with a pH of 6. Okay, so I'm explaining, the scale is logarithmic. So what that means is every time you increase or decrease by a whole value, by a whole integer, okay, you increase that amount by 10. It's tenfold, and then it multiplies by 10. So if we have a substance that's a pH of 6, okay, and we lower it to a pH of 2, okay, 6 to 5 is 10 times more acidic, 5 to 4 is 100 times more acidic, okay, 4 to 3 is 1,000 times more acidic, 3 to 2 is 10,000 times more acidic, okay? So that's how the scale works, and it works like that the other way. So if I have something that's a pH of 8, something that's a pH of 9 is 10 times more alkaline. A pH of 10 would be 100 times more alkaline. A pH of 11 would be 1,000 times more alkaline. A pH of 12 would be 10,000 times more alkaline, okay? So one example I like to give people when I'm doing my demonstration and we're talking about pH, in the pH portion of my talk, I like to show the pH of soda. And I like to compare the pH of soda to the pH of human blood. Okay? Human blood has a pH of around 7.4. Okay? And soda is around 2.5. So if we go from 7.4 to 6.4 is 10 times. 6.4 to 5.4 is 100. 5.4 to 4.4 is 1,000. 4.4 to 3.4 is 10,000. 3.4 to about 2.4 is almost 100,000 times more acidic. So that's a really good way to explain to people how acidic soda is and comparing it to where our blood wants to be. Okay, and then we're drinking this stuff. Okay, what is pH? And if you look how it's spelled here, lower P, capital H is the correct way to spell the abbreviation. Okay, it stands for potential hydrogen. Okay, now people get confused about this because we promote Kangen water as hydrogen-rich water, but there's a difference between the hydrogen that you're measuring when you're looking at a pH of a substance versus the molecular hydrogen gas that's in the Kangen water, okay? People will always get confused by that at first, and that's why we are educating, and we're learning these things so that you will have the answers and give people the peace of mind, okay? So hydrogen is the smallest atom in the universe and has one electron orbiting its nucleus that consists of only one proton. Okay, so hydrogen atom is the smallest atom in the universe. I'm sure if in school, sciences in high school or whatever, depending on what your background is in your school years, atoms have a nucleus which consists of protons and or both neutrons, and we have electrons that orbit the nucleuses, the nuclei, okay? Now, we're not going to get too deep into the different orbits. We're not going to get into some crazy stuff, but as a basic understanding, atoms have a nucleus, and then they have orbiting electrons, okay? And depending on the amount of protons and the amount of electrons orbiting, it's going to change with every atom has its own properties and characteristics. So the hydrogen atom, the nucleus consists of only one proton, and it has only one electron orbiting the nucleus, which is basically a proton. Okay, so protons are positively charged and electrons are negatively charged. So if you have one positive charged proton and you got one negatively charged electron, you have one of each, so you have a net charge that is neutral because they equal. So the charge is neutral. Okay, so another thing to know is that the hydrogen atom very, very, very seldomly, if ever, exists alone in the universe. It's always attached to another hydrogen atom, which gives you diatomic hydrogen or molecular hydrogen, which is the gas, or it attaches itself to another molecule or substance, okay? Just as a tip. When a hydrogen atom loses its orbiting electron, it becomes a hydrogen ion, positively charged. In short, we can say it is a hydrogen proton, or we call it H+. So if the hydrogen atom that has the one proton in the nucleus and the one electron orbiting it, if that electron is lost, a hydrogen atom, okay, is now just the one proton, and it's positively charged because now we have one proton and 0 electrons, so we have a net 1 positive charge. So we call it H+. Okay, and this concentration of H+ in a substance, these hydrogen protons, is what we're measuring when we're measuring pH. Okay, it's the potential of these hydrogen protons in a substance. Okay, the more hydrogen protons in a substance, the more acidic it's going to be. The less hydrogen protons, it's going to be more alkaline. Okay, and that's comparing it to relative to neutral water. Okay. The more hydrogen protons, H+, in a solution, the more acidic the solution becomes. A water becomes acidic when acid substances are dissolved or disassociated in the water. This causes a release of hydrogen protons in the water. The pH of the water will drop due to the increase in hydrogen protons. So if you have pure water, okay, and you add in an acidic substance or mineral, okay, the result of that is going to be a increase of these hydrogen protons, okay, and because of that increase in hydrogen protons, the pH is going to decrease. We're going to lower the pH. Okay. So these positive hydrogen atoms, these are protons. These hydrogen protons are what is creating things to be more acidic. Okay. So that's what pH stands for, potential hydrogen, and it has to do with the concentration of these hydrogen protons. This is a very simple way to look at it. We're going to go in a little bit deeper, okay? Hydrogen protons never stay alone in the solution and will attach to a water molecule. This produces a positive ion called hydronium, which is H3O, okay? So I'm going to take a sip of water. Okay. So we all know what H2O is. It's a water molecule, and it consists of one oxygen atom and has 2 hydrogen atoms bonded to it. Covalent bond. They're called covalent bonds, okay? And what happens is when an acidic substance is introduced to water and it releases these hydrogen protons, like I said before, the hydrogen protons or hydrogen atoms do not stay free. They don't stay alone. So what happens is this H+ will go, it's positive, it will go and attach to an H2O molecule because the oxygen part of the H2O is negative, and then it bonds to the water molecule, producing another molecule called H3O, okay? That's, like we said here, it's called hydronium, and it has a positive charge because it has an extra hydrogen proton. So in short, just so you know, just so you have a deeper understanding, when we talk about H+ or potential hydrogen, we're really talking about hydronium, okay? So if someone says to you, water is just H2O, okay, that is the farthest thing from the truth, and water is a lot more complex than just H2O. So potential hydrogen concentration of H plus in short, but in reality, these H pluses aren't just floating around in water. They are attaching to H2O molecules, creating H3O, which is a positively charged ion called hydronium. And that's what it really looks like. But in short, we'll just say H plus, okay? So here's a picture. So you have the H2O molecule, okay? And we're gonna add another hydrogen, add a proton to it. Okay, so that hydrogen atom lost its electron, so now it's just a proton, a hydrogen proton, and it goes and finds a water molecule, and then it becomes a hydronium, and that's what a hydronium looks like. Okay, and it has a positive charge because it has one more proton total in the whole molecule than electrons. So you have a net one plus, you have a net plus one charge. Okay, so that is actually what the H plus is. And when we say pH and the concentration of hydrogen in the water, we're really talking about hydronium. So the more hydronium a water or a solution has, the more acidic it's going to become. Okay, so what makes something alkaline? Okay, and if you look in this picture, we have another molecule here, or we'll call it an ion because it has a charge. It's called a hydroxide ion. Okay, a hydroxide ion has a negative charge and is written OH negative. Substances that have less H plus, hydronium, okay, than regular neutral pure water, automatically will have more hydroxide, OH negative, okay? And because of that, this having an increase in hydroxide molecules in water will the pH will increase. So when you have less H plus or hydronium, I'm just going to call it H plus for now on, but now we know what it is. So when you have less H plus and you have more hydroxide, okay, that causes the pH to go up. So that's what is making something alkaline. When a solution has less hydronium, H plus, than what would be found in a neutral substance or water, the pH will increase and will become more alkaline. When a substance has less H plus than negative ion hydroxide, OH negative, this substance is said to be alkaline. So there's like a ratio going on here of H plus to OH negative. If you have more OH negative than H plus, it's alkaline. If they're equal, it's neutral. If the H plus is higher than the OH negative, okay, it's an acid. So this is what's going on. So like I said, water is not just H2O. So another way to look at pH is as a ratio of H plus to OH negative. When these two ions are equal, we have a neutral substance. The pH is 7. So the hydronium is positively charged. It has received that hydrogen proton, and the hydroxide is the water molecule that lost the hydrogen proton, okay, but kept its electron and has a negative charge. So why does it have a negative charge? Because in the total molecule or the total ion, there's one, if you were to count up all the protons and all the electrons, you'd have one more electron than proton, so it has a net -1 charge. Okay? So when the H plus and the OH negative equal, okay, the positives and the negatives equal, and you get a net resultant of 0, and you have a neutral. Okay. This may be a new term for most, but it's called autoionization of water. Okay. And this is really, now we're going to be getting a little bit deeper into what the pH scale actually represents. Like, why is it at a 14? Okay, where did it come from? So we're going to kind of get deeper into that information. So naturally, in all water, if you take pure H2O, if you know, like a distilled water, you have 100% pure just H2O. There's a natural process that occurs in water called autoionization. Okay, it's just a natural law. It just happens, and yeah, it's basically what, like I said, this is gonna be getting into, you know, where the pH scale actually came from. So if you look on this picture, if we have pure H2O, okay, we made pure H2O, and if we have, we're gonna have a little bit of autoionization happening in the water naturally. Okay, it's just a universal, it's a natural law, and a very small, it's a very small percentage of the molecules that ionize. But what happens is a water molecule will lose a hydrogen proton, okay, and that hydrogen proton, remember, it doesn't want to be alone, so it will go to another water molecule and create H3O plus hydronium. And the water molecule that lost the hydrogen proton becomes a negatively charged hydroxide because it lost the hydrogen proton. So you end up with, you know, two H2O molecules becoming one hydronium and one hydroxide. And the hydroniums will always equal the hydroxide. They'll always be the same amount. This is what happens naturally in pure H2O, in pure water. Okay? So we'll just look at that one more. We'll just look at that again. Okay? One of the water molecules has lost a hydrogen proton. The other water molecule accepted it. So that water molecule that accepts the hydrogen proton becomes a hydronium positively charged ion, and then the water molecule that lost the hydrogen proton becomes a negatively charged hydroxide. And there will always, in pure water, this autoionization process, when it's happening, you'll always have the same amount of hydronium, or H plus, to hydroxide. Okay, so if you have the same amount of H plus and same amount of that, if you have the same amount of hydroxide to hydronium, okay, and they equal, you get neutral water, zero charge. Okay, we're gonna autoionization. It's important to know that water, H2O, is a deionized molecule. Okay, so when we talk about just H2O, We have the oxygen atom, okay, with the 2 hydrogen atoms. If you tally up all the protons in a water molecule, they will equal the amount of electrons in the water molecule. So the net charge of a water molecule is neutral. Okay, so pure water, okay, has no charge. Therefore, a water molecule is neutral. Okay, the term ionized really means any substance or molecule that has a charge, either positively charged or negatively charged. That is the true definition of ionized. So things can be ionized, positive or negative. When something has no charge, so it's neutral, it's deionized. Hydrogen ions, H+, are spontaneously produced in pure water by the ionization of a very small percentage of water molecules in pure water. This creates an equal amount of hydronium, positive ions, and hydroxide, negative ions, in the pure water. So that's what we just discussed. They spontaneously, the 2 H2O molecules spontaneously become a hydronium and a hydroxide. An interesting natural law occurs where the number of H+ produced in pure water is 1 to every 10 million water molecules. 1 times 10 to the 7. So for every, so when I said it's a small amount that goes on, that spontaneously has this autoionization occurring, for every 10 million water molecules, 1 water molecule is going autoionizing, we'll say. So if we call the total number of water molecules to be 1 unit, then the amount of hydrogen, or H+, ions in the pure water is 1 times 10 to the negative 7. Since there is the same amount of hydroxide ions in the pure water, we can also say that for every unit of water, there is 1 times 10 to the negative 7 hydroxide ions. In short, we say this water is neutral. It has a pH of 7. Okay, so this is where this is why the pH of something neutral is 7. Okay, it has to do with this molecular count, okay, of autoionization happening in pure water. So it's not, they didn't just pick 0 and 14 as a fun scale and then make 7 in the middle. They didn't make it up out of thin air. You know, it's based on this autoionization information here. pH is the negative log of solution's hydrogen concentration. So remember I said it's logarithmic. So if you take that like I said, it's in pure water, you have 1 times 10 to the negative 7 units, okay, of hydronium. Then if you take the negative log of that, it would be 7. So that's basically just what that means. So the pH of a solution is determined by its hydrogen proton concentration relative to pure neutral water. Acids will have hydrogen protons greater than 1 times 10 to the negative 7 m, which stands for moles. And bases or alkaline solutions will have hydrogen proton concentrations less than 1 times 10 to the negative 7 moles, okay? M represents the number of moles of a solute in a liter of solution. 1 mole of a substance is equal to 6.02 times 10 to the 23, so that's 23 zeros after 6.02 particles of that substance, okay? So, like I said, when you're introducing the Kangen water to somebody, or if you're doing a demo, this is not the information you want to get into at a demo about pH, okay? This is not you're going to lose people. They will not understand you. The demo is supposed to be entertaining, is supposed to be educational, but simple. Okay, so people can just get the idea. So they can just get the idea. This is so that you are starting to be aware of the deeper understandings. That way, if people have more intelligent, more in-depth questions, okay, you will have the ability to answer them. Okay? So yeah, so just to recap here, moles per liter is what that 1.1 times 10 to the negative 7 is representing, okay? Okay, example. If we take an acid mineral, such as sulfur, okay, and add it to pure water, the number of hydrogen ions, H plus hydronium, H3O, increases in the water, okay? That's what acid minerals do to water. They increase the hydrogen concentration. The more hydrogen concentration, the more acidic the substance becomes. The sulfur will steal electrons from hydrogen atoms in the water, causing the increase in hydronium. If we increase the H plus by 10 times the amount, the solution will have 1 times 10 to the negative 6 units, okay, compared to pure water. In short, we say the solution now has a pH of 6 and is considered an acid. Okay, so this is where the scale comes from. It comes from this autoionization of neutral water as its reference point, okay? Due to the natural law that exists, the increase in H plus will bring down the amount of hydroxide, OH negative, naturally to 1 times 10 to the negative 8 units. The sum of the exponents between the H plus and the OH negative always equals 14. This is why the pH scale is from 0 to 14. Okay? So technically in every single substance, you can have a pH, and there's a pH and a POH. Okay? Potential hydrogen, potential hydroxide. But to keep things simple and to keep to have a measurable, easy scale to have, we just neglect, it's just understood that when you increase the hydrogen, you decrease the hydroxide. So we don't have to consider the potential hydroxide. So we just stick with pH. Okay? So if I add an acidic mineral to water, I increase the hydrogen protons. So like in this example, we've managed to take a neutral water and we've added sulfur, and now we've got enough hydrogen protons that we've increased the hydrogen content to 1 times 10 to the negative 6 units, so 10 times more. So we end up with pH of 6. Okay, because it's a pH of 6, okay, there's 1 times 10 to the negative 6 hydrogen protons, hydroniums. Therefore, there must be, by natural law, 1 times 10 to the negative 8 hydroxide. Okay, now you have to remember these exponents are negative, so if the negative number goes greater, it means there's less of them. So we're getting farther from 0. Okay, so here's some acid and alkaline minerals. Some examples. So sodium, potassium, calcium, magnesium, manganese, zinc, iron, and bicarbonate, or like sodium bicarbonate, like baking soda. Those are examples of alkaline minerals, substances, okay? Acid minerals, we got nitrates, chlorine, iodine, sulfur, carbonic acids, phosphorus, okay? Phosphates. Those are examples of acid minerals. Another acidic mineral would be fluorine or fluoride. If someone asks you, does Kangen water remove fluoride from the water? No, they do not. Because the fluoride if you live in a city, or if a potential client lives in a city where the municipal water supply is fluoridated, you need to be clear with them and honest that no, the Kangen water device will not eliminate 100% of the fluoride. The 9.5 produced will have less fluoride than the tap water because it's an acidic mineral, so it will go out the acid hose, but not all of it will. Okay? So I recommend for people who live in fluoridated cities who are concerned about fluoridation, a lot of people aren't really concerned about it. There's some people, some people are very concerned about it, some are in the middle, some are not concerned about it at all. Enagic has fantastic fluoride pre-filters, okay, that can be used and hooked up prior to the machine, and that solves the problem 100%. There are also organic acid wastes produced by the body, like acetic acid, lactic acid, cholesterol. That's an organic waste produced by the body. Okay, uric acid, which is produced in the kidneys. Okay, and what produces urine, and fatty acid. Our body will remove these acids by neutralizing them with the aid of alkaline minerals we consume from our food in order to make these acids less harmful to the body while we remove them. Okay, when we are alkaline mineral deficient, we store these acids in our body. Okay, if we can't get rid of the accumulation of acidic waste, organic wastes, okay, there's also inorganic acid byproducts produced by our food, okay, like sulfuric acid, phosphoric acid, and hydrochloric acid. If we cannot buffer these and eliminate them, our body will store them. And this is where we end up with issues like kidney stones and issues like gout, okay, which we're going to get into later. Okay, alkaline versus alkalinity. This is very important because one of the things you're gonna hear a lot of from people who get a little bit of information on the internet from here and there and come up with a conclusion, okay, that alkaline water isn't necessarily safe, is they will tell you, well, I heard from so-and-so that drinking alkaline water will make you too alkaline, okay? So that's a very common question you're going to get. So a water that is alkaline, we now know, has a pH above 7. A water with a high alkalinity has a pH above 7 and also is good at dissolving or buffering acids, okay? Substances with a high alkaline mineral concentration will have a higher alkalinity. They will be able to dilute the acid and bring up the pH, but this will not necessarily eliminate the acid. Kangen water is alkaline but has a low alkalinity, meaning it's a weak buffer. It's not good at neutralizing acids. This is why it takes 32 ounces of Kangen water to neutralize 1 ounce of soda. Okay, so just because something is alkaline doesn't mean it has a strong alkalinity. Like I just said, if something with a low alkalinity is faced in front or mixed with a strong acid, it's not going to raise the pH of that acid. Okay, it won't have the alkalinity to do so. Okay, but if you take an alkaline water, and the reason why it has a high pH is because it has a high mineral concentration, like baking soda. Okay, or if you take a water and you keep adding in more inorganic minerals, so let's say you take tap water, and then you add calcium, then you add some more calcium, then you add some magnesium, okay, then you add some sodium, and then you add some baking soda, okay, you're gonna have something with a lot of minerals that are alkaline, and it's gonna have a high alkalinity, okay? Kangen water, we're not adding any minerals to the water, okay? The only alkaline minerals that are in the Kangen water are the same ones that were already in your tap water, okay? So from a mineral perspective, that's not what's really making the water alkaline. It's the fact that in the electrolysis process, which we're going to get into in a later module, we're really increasing the amount of hydroxide, the OH negatives in the water. So in Kangen water, we have an increase, okay, of hydroxide, which is causing it to be alkaline. Whereas in bottled water per se, or if you are making alkaline water chemically, you're just adding in more minerals, okay? So Kangen water has a low alkalinity, okay, but has a high pH. This is a good thing, as it is impossible to ingest too many alkaline minerals drinking Kangen water. Kangen water is alkaline because it has a high concentration of hydroxide ions, OH negative, not added alkaline minerals. This is not the same for alkaline waters that are not electrolyzed reduced water. They can be harmful. So if you are drinking bottled alkaline waters, if you are making alkaline waters with different types of minerals, that has the potential, if consumed in high volumes, to be harmful, because you're going to be putting in a high concentration of alkaline minerals. Now, yes, most of the time we will pee these alkaline minerals out, but if you are consuming too much of them, you may start storing them in your tissues. You might make your blood temporarily too alkaline, okay? Just like we can become too acidic, there is a potential to make ourselves too alkaline, okay? This is impossible with Kangen water. So if someone says to you, I'm afraid, what if I become too alkaline with this water? You can tell them with confidence, no, it's impossible. Kangen water has a low alkalinity, okay? That's why it takes 32 ounces. It takes 32 ounces of Kangen water to neutralize 1 ounce of soda. So Kangen water has a high pH, low alkalinity, okay? A water that is alkaline due to a high concentration of hydroxide will be able to eliminate acids. OH is a H plus hunter and will combine with the hydrogen proton to create H2O. Acid is eliminated and the body gains a water molecule for hydration. Okay, so this is important. Okay, because you can neutralize acids two ways. One way is you can chemically add minerals. So if you have an acidic substance with a whole bunch of acidic minerals in it, okay, you can add alkaline minerals in it. And because you added alkaline minerals to it, you're not necessarily eliminating the acid, but you're diluting the acid. So because you've changed the ratio of alkaline to acidic minerals, you can alter the pH. Okay? But what the hydroxide does, the OH negative, okay, which is what we're producing with the Kangen water, what it does is the OH negative is negatively charged. The hydroxide is negatively charged, and the hydronium that's present, the high concentrations of hydronium that are present in acid substances are positive. So when a hydroxide is attracted to a hydronium, okay, the hydroxide will take back that hydrogen proton, and you've just taken a hydronium and a hydroxide and converted them back into H2O, into two H2O molecules. So now you have eliminated the H plus, which means you're not neutralizing or diluting the acid, you're actually eliminating it completely. So Kangen water is impossible at making somebody too alkaline, and it is very good at balancing the body's pH and helping the body maintain homeostasis, stay in that balance, that middle area where it wants to be. The pH scale is also a voltage scale. Okay, this is very interesting because, you know, as my background, I'm an electrician, and I really do see the body and the food we eat from an electrical perspective. Okay, we are a bioelectrical being. That's what the human body is, and the pH scale is a voltage scale, and I'm going to explain it here. The definition of voltage is a potential difference between 2 points. Okay, so that's what voltage is. It's a difference between 2 points of energy. Okay, so if I have point A and point B, and point B is 10 points and point A is 5 points, if I take the difference, I have a voltage of 5 between the 2 points. Okay, that's kind of what I'm talking about there. So the 2 points being the difference between the H plus and the OH negative. So that's where we're getting the voltage in the substance. In pure water, we now know that the pH is 7, meaning that it is neutral, because the hydronium is equal to the hydroxide concentration. This means that the water has a 0 volt charge. This is considered dead water. Pure water does not conduct electricity. Okay, so in pure water, your hydroniums equal your hydroxides. So the positives and the negatives are equal, so the voltage, the difference between the 2 points would be 0 volts. Pure water does not conduct electricity. A lot of people grew up knowing and believing that electricity and water don't mix. 99% of the time, they're right. But what's making the water conductive to electricity is not the water itself, it's the minerals that are in the water. So if you eliminate minerals from water, the water becomes less conductive. If you eliminate all the minerals from water and you have pure water, the water is no more conductive than a piece of rubber. Okay? So this is distilled water, pure reverse osmosis water. They're referred to as dead water. They're turned off. They're deionized. Okay, they're aggressive water. They will actually, over time, if they're consumed, they will start to leach minerals from the body. Okay, they're not the best choice for consumption for long-term health. Fish can't even swim or live in a pure water, okay? So the Japanese, like I said, they call it aggressive water or dead water, okay? If a solution has more hydroxide than hydronium, then the water is alkaline, which means it has a negative voltage. The more negative the voltage, the more alkaline the solution. So if I have more hydroxide than hydronium, I have more OH negative than H plus. If I take the difference, I end up with a negative number. Okay, so negative voltages, negative waters equal alkaline waters. If a solution has more hydronium than hydroxide, then the water has a positive voltage. The greater the positive voltage, the more acidic the solution is. So if I have more hydronium and less hydroxide, if I take the difference between the 2 points, I have positive minus negatives, I end up with a positive number. Acids are positively charged, they have a positive voltage, okay? And the more positive, so for an example, if I have so the more positive, the lower the pH will go. The more negative, the higher the pH will go, okay? So as an example, if I have something that's a pH of 8, okay, versus something that's a pH of 9, the pH of 9 will have more hydroxide, which means it will have a greater negative voltage than a pH of 8. Okay, something that's a pH of 2, very acidic, will have more hydronium than something that's a pH of 5, and it will have a higher positive voltage. Acids are electron stealers. So everything's looking for equilibrium. Okay, everything likes to be neutral. Everything's kind of in the universe always looking for equilibrium. So if you have things that are positively charged, they like to take electrons. They like to steal electrons. Okay, that's why acids oxidize things, okay? They steal electrons. And alkalis or bases are electron donors. So negative charged alkaline will donate electrons. Acids, okay, positively charged acids will steal electrons. pH is closely related to the redox or oxidation reduction potential of a solution. And that's going to be another module specifically on ORP, okay? So that's it for module 3 on pH. Okay, let's do just a little recap here. Now, I want to remind you guys, this is a lot more in depth than you want to introduce pH to someone with, okay? But I want to give people the understanding of where these things are coming from, so you will be more confident in speaking about pH. Okay, when you're talking about, okay, the pH scale is from 0 to 14, neutral is 7, okay, it's logarithmic, so if I have something that's a pH of 9, it's 10 times more alkaline than something that's a pH of 8, okay? The blood pH is 7.35 to 7.45, which makes it, slightly alkaline. Okay, you will feel more confident. And when someone asks you questions, okay, that are more in depth, okay, so well, what does a pH mean? Well, now you can say, well, pH means potential hydrogen or hydrogen protons, okay? Oh, okay, so the more hydrogen protons in a substance, the lower the pH goes, it becomes more acidic, okay? You want to have that understanding when you're doing your demos or when you're speaking one-to-one, one-on-one with a new potential client or with a downline who wants to know, because it's going to make you a better leader, but it also is going to give you the confidence to put yourself in the position where you're going to be confronted with questions, okay? Education equals confidence. So, we looked at, what pH means, okay? You've discovered what hydronium is, what the H plus really is, which is hydronium H3O. Okay, we talked about hydroxide, where that comes from, the auto-ionization that occurs in pure water, and that is what the pH scale is basically representing. Okay, the negative log of the amount of hydrogen or hydronium concentration in a substance, okay? So it's a lot of information, and it is very sciencey, but I tried to keep it as simple and as basic as possible, okay? So I hope you guys got a lot out of that. And, you know, if you have to go over it a few times or, you know, look more in depth into this stuff, I recommend you do so. And books, if you're looking for reading, one book I recommend, which will help with this stuff, is a book called Reverse Aging by Sang Wang. And another book called Healing is Voltage by Dr. Jerry Tennant, okay? Okay, so I will see you guys on the next module.